Welcome. We're going to look at the steady state heat equation today. And so that's Laplace's equation, what we have here, but we're going to use finite differences to do that. So Laplace's equation is the second derivative of our function u with respect to x plus our second derivative of u with respect to y equals 0. So it's incredibly simple. Now, using finite differences, we can approximate uxx, the second derivative of u with respect to x, with a step size of h. So h is delta x. And that's also delta y. So 1 on h squared f of x subscript n plus 1, comma, y subscript n, minus 2f x subscript n subscript y plus f x subscript n minus 1, comma, y subscript n. Okay, so here is our approximation of the second derivative of u with respect to x. Similarly, we have one for y. Now let's draw a little diagram of what we have. So say here, if this is the point xn, yn, then over here we might have the point xn plus 1, yn, and back here we have the point xn minus 1, yn. Okay, with this distance between these points being delta x. Remember, equal to that step size h. And similarly here, this is delta x, the distance between these points. Okay, and at these points, we are evaluating our function, except rather than f, I should have written u. So let's put f equals u. We are evaluating at these points. And so we can approximate the second derivative of u with respect to x by taking in these 3 points. Similarly, vertically, we've got 2 points here we could take in to approximate u differentiated twice partially with respect to y. Okay, so let's jump into our problem. Now, I should mention that this problem was created by someone called Graham Chandler, who sadly has passed away. And I remember he said to me, it's got a lot of macros in it, so you might have a hard time compiling that. So I think what I did is just screenshot this one because all of these curly arrows looked a little bit difficult to make. So thank you, Graham. I'm going to use this because I think this is a really instructive problem set. Okay, so our first problem says, consider the steady state heat problem on the grid shown below. So here we have sort of an L-shaped region where the heat equation applies. And remember, it's difficult to solve such a problem analytically because we can find functions that satisfy Laplace's equation, but it's difficult to find functions that satisfy both Laplace's equation and the boundary conditions. Okay, so this says on the diagram, fill in the known temperatures at the grid points on the boundary. So we begin there. So we just look at the functions that we have on the boundary. Now, we can see from reading this that this x value here is 3/4, for example. And we have 1, 2, 3 of those. So then delta x, the distance here, must be 1/4. So if I take 1/4 and sub in there where I have that x, now this says ux comma 1, so when y is 1, this is equal to 60 times 4/3 x. So here I would sub in 1/4. And so 4/3 times 1/4 is 1/3. 1/3 of 60 is 20. So we've got 20 degrees there. Presumably this is in degrees centigrade. Okay, now here we would have x value 1/2. So if we sub in 1/2 there, then we have 40 here. Okay, now if I put in 3/4 for x, 4/3 times 3/4 is 1, and so here I would get 60. All right, now this says that along this side we have 60, so we have 60 here as well, and we should have 60 in the corner. We should have 60 here, and likewise 60 here. Okay, now along this right-hand edge, we have u of 5/4, comma y equals 60 times 2y. So here the y value is 1/4. And so subbing in 1/4, 60 times 2 times 1/4 is 60 times 1/2. And so that's 30. And then here down the bottom, y is 0. So we just have a temperature of 0 down the bottom. Okay, and now along the left side and the bottom, we have temperatures equal to 0. So we've now done part A. Okay, so now recall what we had here on this page. We had approximations for uxx and uyy. Now, if we add these together in Laplace's equation, we can get an approximation of Laplace's equation, but then if we multiply throughout by h squared, that would vanish because we have 0 on the right-hand side. Notice that a couple of these things would add. Notice that these two things are the same and hence would add together. So Laplace's equation is approximated by the expression f xn plus 1 yn minus 4 f xn yn and then plus one of the rest of them. Okay, and so with this, we can think about this geometrically using what we call a template. So in the middle, we have our point xn, yn. Out here, we have xn minus 1, yn. Here we have xn plus 1, yn. Then here we have x n yn plus 1. And down here we have xn yn minus 1. Okay, what are the coefficients of these? We have a coefficient 1, 1, 1, 1, and minus 4. So we can think of this as a template that we just put over those points and write down a linear equation. And so that's what we're going to do on the interior of the template here. So I think what I need to do is cut out a little template that matches this. Okay, let's see if I can do this with my fingernails. And then, you know, I really want to cut out this so it looks like that cross-shaped template. You should probably do this too. Until you get the hang of this. Okay, so something like this thing, all right? So what we're going to do is we're going to take this, write down the equations that we get from taking these into consideration, then we move it over, and then we move it over and over and over and over and over until we've written down several linear equations. Okay, so let's first label our equations. Okay, and so I'm going to go with calling this one here U13, U23. Notice my subscripts indicate where we are on the grid. Okay, so next U12, U22, U11, U21, U31, and U41. Okay, so next let's write down our equations. So that is on my next page of the worksheet. Okay, so here, so what I'm going to do is bring that into view. So that you can see this also. Okay, so beginning up at the top, so we have, how do I want to start this? You got to think really carefully about what you want to have down here in this column, right? And so I think I want to have U11, then U21, U31, U41, U12, U22, U13, U23. Something like this, right? And so when I write down the equation, I need to set out some spaces so that they match up with this and I can get a matrix equation. All right, so let's write our equations. You know what? I think I'm just going to have to write it small down this column so we could fit everything in place. Okay, so the first one, when I put this template over this, we're looking at 0 plus 20 minus 4 U13 plus U23 plus U12 equals 0. Now, what you can do with this is take that 20 over to the right-hand side. And so where is the minus 4? It's next to the 13. So I'm going to come down to this row and put that here so that the 4 appears in the correct position. Okay, so for this equation, because I started in the top left, I'm going to come down here and put a minus 4 there. So this would say, once we multiply this out, minus 4 times U13, which corresponds to that. Okay, now in that row, we would have a 1 for the U23 entry. So that's here. And a 1 for the U12 entry. And so that's the 5th entry. So that's here. And zeros everywhere else in that matrix row. And then on the right-hand side, we're taking that 20 over We have minus 20 there. Okay, and so now let's move our template over to the next one, where the minus 4 appears over the U23 entry. Okay, so that is here. Now what is around that? We have 40 plus 60, but then we're going to take that 100 over to the right-hand side, and we would get minus 100 there. Okay, the other letters are U13 and U22. So 13, so put a 1 in the second last column of that row for the U13, and then U22, that corresponds to here. Okay, and now I'm feeling a little bit skeptical because I'm expecting a symmetric matrix. So I want to double check the last one we wrote down. So U12, U23. 1, 2's there, U23 is the last one. Okay, sure. So zeros everywhere else in that row. Okay, so we've done the top here. Now we come down to here and do this. Okay, so minus 4 next to the U12. So where is that? Here. And then that takes in U11 and U22. Where are they? 11 is the top, so here. 22 is there. And zeros everywhere else in that row. Okay, now for the right-hand side of that, the only number that we add is 0, so we just have a 0 here. Okay, great. So next, let's scoot this over to U22. So minus 4 next to U22. And so we're taking in U21. And we are taking in U12. We're taking in 60 and U23. Zeros elsewhere in that row. Now the 60, we'll take that over to the right-hand side of the equation and we'll write minus 60. Okay, and so we keep moving this template along and write down our other equations. So I'm just going to fill those in for you. We have minus 4, 1, 0, 0, 1, 0, 0, 0, and 0. Okay, next, 1, minus 4, 1, 0, 0, 1, 0, 0. And for that, we have 0 on the right-hand side. Okay. Third row, 0, 1, minus 4, 1, 0, 0, 0, 0, and minus 60 on the right-hand side. Okay, next we have 0, 0, 1, minus 4, 0, 0, 0, 0, and minus 90 on the right-hand side. Okay, so we have a matrix equation that we got from Laplace's equation by approximating it. So the next thing you would want to do is notice what kind of matrix you have. You have a symmetric, diagonally dominant matrix. And there are special methods in numerical linear algebra for solving those. Question 2. Consider the problem of determining the steady-state heat distribution in a thin rectangular metal plate with dimensions 0.3 meters wide by 0.5 meters high. So look, the first thing you would want to do here is draw a diagram of this metal plate. So let's do that here. Leave some space to do some mathematics. Okay, and so that's the height of it. Maybe I should even measure this thing in centimeters if I can. 8 plus 5. Yeah. 1, 2, 3, 4, 5. Yeah, 8 plus 5 is 13, so that looks fine. Okay, and then what did we see? Say 0.3 wide. So if I do 3 centimeters wide, then I'll have a nice diagram to scale. Okay, so let's fill in some grid points here. And I'm just going to guess about where these should be. Okay, and so let's label this U11. Then we'll label this U21, U12, U22, U13, U23, U14, and U24. So there are 8 interior grid points there. Okay, so now we are told that when y is 0.5 meters, so that's up at the top, the temperature is 30. So then we should have 30 here, 30 here, 30 here, and 30 here. Okay, now how about at the bottom? Now along the bottom, this bottom is governed by x comma 0 is x squared plus 15x plus 39. And so we would have to calculate what these are at these x values to fill in what it is at the bottom. Okay, now our step size in this case is 0.1 meters. So let's begin by calculating what we're going to get down the bottom. So when x is 0, we have 39. So 39 for this. Okay, so if we sub in 0.1 for x, okay, so I've just opened up Mathematica, and what I'm going to ask it to do is calculate what this function is when x is 0.1. So I'm just going to enter that into memory. And then after that, let's clear that value. Okay, so 40.51. Okay, and now when x is 0.2, we have 42.04. And when x is 0.3, we have 43.59. Okay, now let's go back to our problem. So next we read that when x is 0, so over here on the left side, we have 39 minus 18y. And so back to Mathematica, where we're going to enter this function, 39 minus 18 times y. Now look, there are a few to enter here, so I'll just tabulate this to make a nice little list of what these numbers are going to be. So we'll tabulate this over y as y goes from 0 to 0.5 in steps of 0.1. 29.5, it doesn't quite match that, does it? Is that because I've entered the wrong function? Yeah, I've entered the wrong function, so I better do this again. Okay, so 39, 37.2, 35.4, 33.6, 31.8, and 30. Okay, so the corner matches there. Now on this side, so we have t of 0.3 y equals minus 40y squared minus 7.18 y plus 43.59. Okay, now when y is 0, we have 43.59 matching with that corner, so that's fine. Okay, so let's try this trick again. I'll just change the inside function there to be minus 40y squared minus 7.18y plus 43.59. Okay, and so we've got 43.59, 42.472, 40.554, 37.836, 34.318, and 30. Okay, so we have all of the boundary grid points. We know the temperature at those points. So next, what we need to do is use the template approximating Laplace's equation to write the temperature of those interior points. And so let's write these linear equations here. Okay, so beginning down the bottom, minus 4u11 plus u12 plus u21 plus the sum of these two. So we need to know 37.2 plus 40.51. And so we get 77.71, which would be plus here, but let's take that over to the right-hand side while we're at it and write minus 77.71. Okay, and so let's move on to this grid point, putting our template over U21. So we have minus 4U21 plus U11 plus U22 equals minus the sum of these two. And so we have 42.04 plus 42.47. And I've just rounded that to 2 decimal places. So minus 84.51 when we take that over to the right-hand side. Okay, next, let's take our template over the U12 entry. So we have minus 4U12 plus U11 plus U22 plus U13. This is equal to minus 34. I think that was 0.4, wasn't it? Yeah. No, 35.4. Okay. Next, we'll place it over this U22, so minus 4U22 plus U12 plus U21 plus U23 plus 40.55 equals 0. So we take that 40.55 over to the right-hand side. We get minus 40.55. Okay, next we'll place our template over U13. We have minus 4 U13 plus U12 plus U23 plus U14 plus 33.6 equals 0. So we take the 33.6 to the right-hand side, and we have minus 33.6. All right, next, let's take that template over U23. So minus 4 U23 plus U13 plus U22 plus U24 equals minus 37.84, rounded to 2 decimal places. Okay, putting our template over U14, we have minus 4 U14 plus U13 plus U24 plus 30 plus 31.8, so plus 61.8, and so this is equal to minus 61.8. Okay, now putting our template over U24, we have minus U24 plus U14 plus U23 plus 34.32 plus 30 is plus 64.32, but we take that to the right-hand side and we have minus 64.32. Okay, so now we've written all of our linear equations, so the next thing to do is write a matrix equation. Okay, so now that we have our 8 linear equations, we can write down an 8 by 8 matrix times an 8 by 1 matrix equals an 8 by 1 matrix. All right, so let's do that here, but it's going to have to be written pretty small. So something like this. And the first thing you want to do is set out the position of your variables. So let's put U11, U21, U12, U22, U13, U23, U14, and U24. And because this is getting fairly large, it's not a bad idea to draw yourself some lines. You know, at least for 2 by 2 blocks. Something like what I have here. So you should do the same with yours. All right, so let's fill in where we have the minus 4 next to the U11. We'll have minus 4 up in that top left corner. And then in that equation, we have U12 and U21 next. So the U21 is next. That's second here. So we have a 1 there. Where is the U12 in this? It's third. So there, and we have zeros everywhere else. Okay, now the right-hand side of that is minus 77.71. Okay, so next equation, minus 4U21. So that's the second entry of this matrix. So we go over here to the second column. Okay, what else do we have? U11. So 1 for that. And U22, that's in the 4th position here. So the 4th position of this, or the 4th column, put a 1 in that row. And zeros everywhere else in the matrix. And then on the right-hand side, we have minus 84.51. Okay, so we come down to our third one, minus 4u12. So that goes there. u11, it's way over here. u22, that's fourth. u13, that is fifth. And zeros elsewhere in that row. And then on the right-hand side, we have minus 35.40. Okay, fourth equation goes in the fourth row. So minus 4u22, u12 is third, u21 second, u23 is sixth, and zeros elsewhere. The right-hand side of that equation is minus 40.55. Okay, so we've done the first four equations. Let's go to the fifth one, minus 4u13. Now this is the fifth position. 1, 2, that's third. 2, 1, second. Oh, hang on, am I reading the right one? So 2, 1 is not there. Where did we put that? Yeah, so that'll be a 0 here. Okay, 2, 3 here. 1, 4 is here. Okay, so we've done that. This equation, minus 4u23. Okay, so that goes here. u13 here. u22, fourth position, so here. u24, the last position, and zeros elsewhere. Okay, seventh equation, minus 4u14. u14 is in the seventh position, so minus 4 there. u13 is fifth position, so here. u24 here, and zeros elsewhere. Okay, last equation, which I think is wrong because I should have a 4 in there. So let's go back and have a look at it. So minus 4u24. There we go. Okay, so minus 4 there. u14, a 1 there. u23, 1 there, and zeros elsewhere. Now, we've neglected to do the right-hand side of these last equations, so we got to fill in those numbers. Okay, and we have completed the question now because we've got our matrix equation. That's what we're asked to do there. And of course, you solve this numerically because it's getting fairly large. It's large, diagonally dominant, and symmetric. And so you could use Gauss-Seidel, you could use successive over-relaxation, and you could use conjugate gradient method. Okay, question 3. Consider the problem of determining the steady-state heat distribution in a thin triangular metal plate with width and height 4 meters, the temperature U of X and Y along the 3 boundaries of the plate are given by the 3 equations right there. Okay, but there are a couple of typos here in my PDF, all right? So they should be the points 2, 1, 3, 1, and 3, 2. So let's write a little diagram here. So we've got a right triangle. These side lengths are equal. And we know that because this boundary says UXX. So that's the line Y equals X in space. Okay, and so along this boundary, we have U, XX is 40 minus 3x squared plus 4x. Now along the bottom where y is 0, we have ux0 is x squared plus 40. And then along this side, we have u4y is 56 minus y squared minus 8y. Okay, so our grid points now, it says the coordinates 2, 1, 3, 1, and 3, 2. Right? Having a look at this rather than what's on the PDF. So we slice it like this. Okay, and so we have, oh, hang on, I need another slice, don't I? Okay, so we're going to label this one U21. Label this U22. This one I'll label U23. So we have 3 interior grid points of unknown temperature at this point. So again, we'll want to start with our boundary. So I'll open up Mathematica to fill in those boundary values. Okay, and so I'll first enter that function that's on the diagonal, and then I'll just tabulate over x. Okay, as x goes from 0 to 4. So we have 40, 41, 36, 25, and 8. So 40, 41, 36, 25, 8. Okay, now let's do the bottom. So that's 40 plus x squared as x goes from 0 to 4. So 40, 41, 44, 49, and 56. Okay, now on this side, we have 56 minus y squared minus 8y, and that's y going from 0 to 4. So 56, 47, 36, 23, and 8. Okay, and so now we apply our template. So let's begin with this bottom one. So minus 4u21 plus u22 plus 44 plus 41 plus 36. Now 44 plus 41 is 85. 85 plus 36 is 121. So we take that over to the right-hand side and we have minus 121. All right, so we've applied our template here. Now let's move it to u22. So minus 4u22 plus u21 plus u23 plus 49 plus 47. Now the sum of 49 and 47 should be 96. So taking that to the right-hand side, we have minus 96. Okay, applying our template on u23, minus 4u23 plus u22 plus 36 plus 36 plus 25. And 36 and 36 is 72. 72 and 25 should be 97. Taking that to the right-hand side gives us minus 97. Okay, now it just remains for us to write a matrix equation from this. So that'll be a 3 by 3 matrix times a 3 by 1 matrix equals a 3 by 1 matrix. So we start with the entries in the column. What variables are we going to put? So we'll put u21, u22, and u23. Okay, and now reading from our first equation, minus 4 times U21. Then we have plus U22, so that's a 1 there and a 0. And on the right-hand side, we have minus 121. Second equation, minus 4 U22, so that's here in the middle. U21 there, U23 there, equals minus 96. Okay, last equation, minus 4 U23, that goes here. U22 here, and then a 0 elsewhere, and minus 97 on the right-hand side. Okay, so we have our matrix equation, and it just remains to solve that. You know, because this one is small, I can get Mathematica to do that for me, so why don't I do that? So first I'll enter a matrix, minus 4, 1, 0 is in the top row. Then we have 1, minus 4, 1 in the second row. In the third row, 0, 1, minus 4. Okay, so I can display this as a matrix if I like, and it looks just like that. Okay, so next, I want to take the inverse of that. Now, you wouldn't do this ordinarily for a numerical analysis problem because taking an inverse of a matrix is very expensive. This matrix is small, but it's diagonally dominant and symmetric. So if it were bigger, you would want to use a numerical analysis matrix approach for solving that linear system. You know, conjugate gradient, successive over relaxation, and so on and so on. But this is tiny, so it makes sense for me to take the inverse of the matrix A and just multiply by the column I have here on the right-hand side. I'll enter those numbers. And I'll press the button, and so we get, just by solving that system, we've got U21 is 41 degrees. We have U22 is 43 degrees. And we have U23 is 35 degrees. Okay, and so that 35 is somewhat close to the neighbors there in temperature, so that seems reasonable to me.